Okay, well then that's fine. Chemistry time, that's fine. Chemistry time, we are on. We are talking today about the mole.
The one that grows on your body, or
The mole. Yeah, you would have already known the answer to that question if we had had school on October 23rd. That's an important date for it to be Mole Day. There's a chemistry celebration called Mole Day about this number, the mole. And one of the songs that we sing, just like you have Jingle Bell or Grandma Got Run Over by a Reindeer at Christmas time, and The Ghost of John at Halloween. I don't know what other things people sing at Halloween. On Mole Day, we sing a song called the Mole Song. And one of the lines, in fact, the first line is, "A mole is an animal that burrows in the ground, or a spot on your chin that you've got to shave around. But there's another kind of mole of interest to me, and that's the kind of mole they use in chemistry." And that's how it starts, and that's what we're talking about today, is this mole.
you should start your video.
I just did. Okay. What is a mole? Well, you should know the definition of the mole already from your vocabulary. A mole, as that song goes on to say, is a unit. A mole is not a unit really like a kilogram. Like, it's not something we measure things with per se. It's more of a unit like a dozen. You can have a dozen of anything, can't you? Could you have a dozen fingers? Yeah, you can have the 10 on your body, and you could have 2 in your mouth from someone else. I don't know your life. You could have the 10 on your body, and you could have 1 in each pocket that you got from a homeless person. I don't know your life. But you could have a dozen fingers, could you not? Could you have a dozen teeth? Yeah, there are people in this town who have only but a dozen teeth. Could you have a dozen Cap'n Crunch cereal pieces?
Yes.
Heck yeah, you could. A dozen doesn't mean it's a certain thing. It means a certain number of anything. It's the same way with a mole. Except instead of 12, which is a dozen, a mole is 6.02 times 10 to the 23rd. And this is sometimes called Avogadro's number. Yeah, hopefully you did. Named after Amadeo Avogadro, I think British scientist. He might have been Italian. I can't remember. Might have been Swiss even. It doesn't matter what his nationality, but it's named after him. And he discovered, or is said to have discovered, this relationship between the molecular mass of something and how many atoms it contains, which is a very, very, very useful, not even abbreviation, but like switch back and forth, because we can measure molecular mass. We can't. It's very difficult to measure how many atoms, because unlike a dozen, I can't count. If I do have a dozen, I can't count the fingers on my hands and the ones that are in my pockets and get to Avogadro's number, right? If I had a mole of fingers, probably way more than planet Earth. This is a huge number. It's an enormous number. And so we can't, like a dozen, just count the things. We have to use some other proxy to find out how many moles of something there is. And so most of the time we use this idea of molar mass. Molar mass. And we talk about how each element on the periodic table and the substances that are built from those elements have a particular molar mass, measured in grams, usually grams per mole. Could we measure it in kilograms per mole? Sure, that's the way units work. Of course we could, but we usually measure in grams per mole. And we can convert back and forth. These are all going to be unit conversions. In fact, from here on out in the year, it's pretty much unit conversions all the way down. But that's okay because you're good at those. So what we do is we can convert from moles to mass using the molar mass. See how this fraction would allow us to convert from grams, a mass unit, to moles, an amount.
So the number of moles times mass in grams over 1 mole.
Yeah, we're going to do it as a unit conversion. So if I had, for instance, let's say I had, here's an example problem, 7.3 times 10 to the 22nd atoms of silver. And I do insist that you keep whatever substance you have as a unit as part of the unit, because we're going to be, right now we're converting from atoms to grams, or atoms to moles and moles to grams eventually. I think at this time we'll just convert to moles. But pretty soon we will be, the whole point of chapter 11, which you'll astute understanders of the number line will see that is the next chapter. we're going to be converting from atoms of one thing perhaps to atoms of another thing. And so atoms and atoms are both the unit, so we want to keep the substance with it. This is one of many examples of it, when it's easy to do it now, so let's do it now, whereas pretty soon it's going to get hard, and if we already do it when it's easy, it'll be easier when it's hard. So we're going to start with atoms of silver. As with any unit conversion, we want to eliminate atoms of silver by putting on the opposite side of the fraction delineation bar. So it's in the numerator here. How do I know this is the numerator? Yeah, it's understood to be over 1. If it's just a number, that's the same as that number over 1. And so in order to eliminate this unit, atoms of silver, I want to get it in the denominator. So what should be in the numerator? Well, if I'm trying to get 2 moles, I want to go to moles of silver. And this is always going to be easy. Let me do another example here. Let's say that no matter what, and this is a little bit ableist, but let's say that no matter what, 5 fingers makes a hand, okay? And I've got 12 fingers, as I said. Okay, I've got 10, and then I have one from each of the homeless people I killed on my way here in my pocket. So I've got 12 fingers, and I want to figure out how many hands I have, right? This is another unit conversion. I've got 12 fingers to hand. What did I just say the unit conversion is? 1 hand is 5 fingers. How many hands then do I have? 5 divided by 12 over 5 is 1.2 hands. That's not right, is it? 2.25, so 2.4 hands. But we're saying here that 1 hand is always 5 fingers. If I had 36, we'll just use eggs. If I had 36 eggs, doesn't matter what the thing is. 1 dozen is 12 of that thing. We've got 3 dozen eggs. Same thing up here. It doesn't matter what substance this is. 1 mole is always how many atoms? Or, sorry, how many particles? In this case, it's atoms. 6.02 times 10 to the 23rd. Unlike these where I struggle a little with this math, this one was easy. Unlike these where you can do them in your head, ain't no one going to be doing 7.3 times 10 to the 22nd divided by 6.02 times 10 to the 23rd. It's not really hard. It's just, not right now we're not. No, it isn't. And hey, would someone get their calculator out? I'd like 2 people to have their calculators out so we can have a corroboration, so sure that we got it right. And that's fairly visible on the screen, I would say. This new color is, what's the new color? Orange. An easy way to type these in, by the way, this is as good a time as any to say this. Great way, I think, to type these in. I would type in these exact characters on my calculator. Try it out, even if you've already got one. Someone keep it up, but I want everyone else to try it out. 7.3 second comma. See the comma there? And that should have a little E. See that little E, baby? So I type in these characters. 7.3 second comma, which gives me E, 22. And that's this. That's that whole thing. And then, if you use it that way, you can just press the division sign and divide it right away by 6.02 E23. Instead, if you're doing it this way, you have to put in parentheses 7.3 times 10 raised to the 22nd power divided by, in parentheses, 6.02 times 10 raised to the 22nd power, or 23rd power. That's just more characters. It's easier to use the E. What do you end up with? Yeah, anyone? Okay, 0.121 watts. Well, we eliminated atoms of silver, and we're left with moles of silver. Would it make sense, if 1 mole is 6.02 times 10 to the 23rd, would it make sense for this number to be less than 1 mole? Well, sure, because we have a whole order of magnitude less than we do of a mole. What have we converted here? From what to what? In this case, it was atoms to moles. We call this kind of conversion particles. And let's have a little side note over here. Each kind of species in chemistry has its own particle. So this kind of math is called particles to mole. And we have different particles. So if it's just an element, what is the elementary particle of an element? What's the most basic unit of that element? An atom. What if it's a covalently bonded substance? What's the most basic unit of that? What's the most, so let's say it's CO2, that's covalently bonded. What's the most basic unit of CO2? Is it an atom? No, because those carbon and oxygen atoms are not CO2. So it's a what? Remember what it's called for covalent bonds? A molecule. So the most basic unit of that substance is a molecule. For an ionically bonded substance? It's called a formula unit, often abbreviated FU. There's another one too. What was the other one? Well, that's good enough for now. But basically, if you see it, say, for instance, you wouldn't want to put atoms, if this were not silver, if it were instead silver chloride, which is ionically bonded, we wouldn't put atoms of silver chloride here, because that wouldn't be true. How many atoms are in silver chloride? Well, in the individual substance of silver chloride, there are 2 atoms. There's silver and chlorine, right? So this wouldn't be true of that. So the individual units of that would be a formula unit, which is why we use these different. And it is important to use these different terminologies because, like I just said, in the case of silver chloride, AgCl, there's twice as many atoms as there are formula units because every formula unit contains 2 atoms. So we wouldn't want to use this when we're using the particle, when we're doing the particle math for that substance. You use the most basic particle that makes up that thing, not always atoms. Okay, so it's not always moles to atoms. The next thing we can do is a similar thing, but this time using, I'm going to erase these 2 kind of silly examples. For the record, I do not actually murder homeless people. I just take their fingers off. I leave them living. So for the next kind of math, we can now we can convert it to mass using the periodic table. So let's say we have, and this is nice because we can do it experimentally. Let's say we have 71.3 grams of water. We could go get that in the lab, couldn't we? I mean, you can think of a procedure where we could actually go fetch that up, right? That would not be hard. This is something really measurable. And this is why Avogadro's number is so powerful. Because we can take this thing that we can really measure and we can say, well, this is how many, in this case, molecules are in it.
Do we know how many, we put 1 mole over how many grams? How do we know how many grams?
Yeah, we're going to get there in a second. So we want to, since this unit is in the numerator, we want to get it in the denominator. So grams. You don't have to write out grams. The abbreviation is G. Maybe I should do that too, sorry. Nope, we keep H2O down here. We wanted that to be with the H2O. What are we trying to go to, though? I didn't even tell you yet, but we're going to go to moles. We'll pretend the problem said go to moles of H2O. How many grams are in a mole of H2O? Well, for things that are on the periodic table, you can just look at the molar mass. That's why this number is so important. In physical science and in the beginning of this year, we found that we can't use this number for finding how many protons, neutrons, and electrons are in an atom. And at the time, it seemed like, why would we even have this number on here? Well, it's because of this. This is something we do much, much, much more frequently than that other thing. And this is a much more important number because, basically, these are not whole numbers. Because when you get a lump of silver, some of them are silver. I don't even remember what the isotopes are, but some of them will say are silver 107, one are silver 108, some are silver 109. Those are the different isotopes of silver, say. I don't know for sure, but we'll say those are the different isotopes of silver. But when we have a lump of silver, it's all those mixed together with the same ratio everywhere pretty much in the universe. Anytime we have a buttload of silver, it's going to have approximately the same ratio, and this ratio ends up being 107.868 is the average atomic mass, which we can use that number to find out how many grams there are in a mole. Is it just a miracle that grams per mole is the same as the mass number of these individual atoms? No, that's how we define mole. That's how those things were defined. So, if it's on the periodic table, we can just get the number right from the periodic table. But this one's not, and so we have to show, as a separate step, hydrogen and oxygen's molar mass. So hydrogen is 1.0079. Where do you get that from? I pulled it from my head, but I have it memorized from the periodic table. You can use the periodic table as much as you need. And then oxygen is 15.999 grams per mole. Please do put units with these. People sometimes don't want to because they feel lazy. And then H2O. Hey, what do I have to do though? This isn't going to quite get me right there, is it?
Add two hydrogen together and then add the oxygen.
Yeah, if I'm going to add 2 hydrogen together, an easier way to do that would be multiplied by 2. I like to put that after the unit. This is not a hard and fast rule. So basically we end up with, if someone wants to do this math, 1.0079 times 2 plus 15.9999, sorry, just 3 nines, grams per mole. It ends up being, obviously this is about 1 times 2 is 2. This is almost exactly 16. It ends up being about 18, probably 18 point, what, 0.15-ish grams per mole. Notice this unit, grams per mole. I wrote it the way I usually do. I'm going to write it a different way now. Grams over mole. That tells us how many, in 1 mole, there are that many grams. Do you see how this thing is the same as?
18.0148.
Do you see how these two things are the same? Yes? Are you with me? Tiana? Yeah? Okay, so those two things are the same. So what do I put on this line?
So
1 mole is,
18.01.
yeah, and by the way, corroborate that math because I just did that in my head. Is that about right?
0.14.
0.
148.
0.148?
0.01.
18 point?
18.0148.
Okay, so I was right. I just had rounded it. Nice, thanks. Anyway, this is not a part of the problem. I just ran out of room because of my little side note here. You do have to show this every time. This is not a side note. You have to show this every time that you're adding them up. Once you get going, it really does not take that long. This is the kind of decimal addition you do in like 3rd grade. So you'll remember that. Now, for the actual method we want to do, 71.3 times 1, still 71.3, divided by 18.015 is, well, what's our unit going to be first? Grams reduced to 1, we're left with moles of H2O. What's our number of moles?
3.9.
3.96 moles of water. So if we went into the lab right now and we filled up a graduated cylinder and massed it to be 71.3 grams of water, which we could do. We could do that right now. We're not going to because it would be kind of a waste of time. But we would know that it contains 3.96 moles of water. And that's powerful because that tells us how many atoms are in that bucket because it's always the same. Does that make sense? Why is it always the same? Well, this measures amount of atoms. Each atom has its own individual mass. So if we have a certain amount of atoms, they will always have the same mass. That's how mass is defined. Remember, mass is amount of matter in an object. This is telling us number of atoms in it. This is telling us how much matter there is. They're the same. We can always do this conversion as long as we know one or the other. Why would we ever want to? Why would we ever want to get to moles?
So what math would you do to find the amount of atoms?
They're intermixing.
Oh, and that you mean if we wanted to go from this to the one like this, we can just chain them. Is that what you're talking about? Like if we wanted to get to the actual number of atoms instead of just this many moles? Sure, let's just do it from there. Let's do the same problem this time getting to number of atoms. 71.3 grams of water. Let's chain them. Tell me what to write first. So that's our given. What should I do first?
Write the units.
Yeah, put the units in. So what unit should I put in first? We want to eliminate or we want to reduce to 1 grams of water. Going to, we want to eventually get to atoms, but we can't just go right from grams to atoms because that isn't set. Because some things, obviously since these numbers up here are different, we can't just go for anything from grams right to atoms with a single number. We have to be able to find the number of moles first. This is like, you can kind of think of this unit moles as like the great equalizer. Like it allows us to use all the same kind of math with all of these, even though they have completely different atomic masses. So grams to moles of water, someone had said, and that's correct. And then from moles to but it's not atoms because it's water. There's no atom of water.
Molecules.
But thank you for pointing that out. Yeah, molecules. You can either write molecules if you're feeling lazy. You're not supposed to feel lazy, but you can always just use particles of H2O. I'm going to put that there just to show you that you can. In fact, several of the problems in your chapter of U have you convert to, it'll say, find the, this is called the representative, I should have written that down, representative particle. One of them might even say, the following is a list of masses, find the number of representative particles. So you have to not only do the math, but tell what kind of representative particle it is. So you would correctly put molecules there, but particles is also right, it's just like less specific. Now we can put our numbers in. In every, just like before, in every 1 mole of water, there are 18.015 grams of water. And then this one, don't get tripped up because people do this all the time. They're always accidentally using Avogadro's number here. This is the molar mass. If we had just started this problem, we'd have to show this again. Since we just did one with it, I'm just going to leave it up there. But this is how you find molar mass. What do we put on these lines? How many particles of H2O are in a mole of H2O? How many hobo fingers are in a dozen hobo fingers? 12. It's the same kind of problem. There's always 6.02 times 10 to the 23rd particles in a mole. That's the definition of a mole. But that's the only one where we use Avogadro's number. Okay? So now we'll be left with, we're going to reduce out our grams, moles, we're left with particles. I'll write it right this time, molecules of water. Math it up. We're going to get a very large or a very small number for this before we even do the math. What do you think?
Oh, very large.
Yeah, it's going to be very large, and we expect that to be because we're talking about a macroscopic amount of water. Like I can see this amount of water and how many atoms are in it. So it's going to be an enormous number. What'd you get? So she's pointing at it, but she means to say out loud, I'd call that 2.39 times 10 to the 24th. 2.39 times 10 to the 24th molecules of water. 2.39 times 10 to the 24th molecules of water. So this actually, the camera's not going to be able to pick this up because my cup is opaque. Hello, here's my opaque cup. Slightly emptier than it was a second ago. I'm going to put in, that's probably not quite 71.3 milliliters, which by the way, for water, grams and milliliters are the same. Hey, you can see in there, and this is not just water. Understanders of liquids will surmise. This is not just water, this is tea, but it's mostly water, and there might be there's somewhere within an order of magnitude of 2.39 times 10 to the 24th molecules of water. Do you see how that's powerful? Like that tells us how many atoms. So here's where it gets interesting, and this is the next chapter, is that when a reaction occurs, because we know how reactions work, right? The atoms are disconnecting and then reconnecting. This happens on this scale. So by knowing this, we can tell how many of those will be used in a reaction, and that can tell us how many we can expect. And so we use this on like industrial or factory scales where we say we're going to mix together X amount of, I don't know what things people might mix together, X amount of Barbie doll serum 1 and Y amount of Barbie doll serum 2, and when we mix them together, we get the exact perfect Barbie doll. Well, how would anyone ever know? It's not just trial and error. They do this kind of math to figure out what is that exact perfect ratio. Barbie doll. I don't know where that example came from. I think... Oh, yeah. Last thing is we're going to talk about empirical and molecular formulas. Your book also talks about formulas of a hydrate. My goal was that we would do that lab, and that would tell you about how hydrates work. And so that's, if you need more, we can talk about it. And as you're doing your chapter review, it'll become apparent whether you need more or not, and we will talk about it during the chapter review. But let's do this last thing before we close. Probably just start by erasing this first one that Swanee was here for, so that when he comes back, he was here for this one. So I'll leave this bottom one so that he can still see it, and I'll leave this part because that's also part of the bottom line. I'm going to switch colors so that he can tell what he missed and what was already here. I'll go to. I like this millennial teal color, so I'm going to use this one. And this is called empirical and molecular formulas. It's just, this is a subheading. It's still about the mole. Empirical and molecular formulas, or as I like to put it, formulae with an E at the end is I think the correct or the correct pluralization of the word formula. That's from the Latin. Percent composition is something we've already done before, but we're going to kind of review that here. Let's look at the example on page 343 if you want to follow along. I'll hold it up for the camera in case you're watching this in the future, or, well, you are definitely watching this in the future to me because this is not being live streamed. So we're going to do this example on page 343 here. If you want to pause it, you can look. It says, sodium hydrogen carbonate, also called baking soda, is an active ingredient in some antacids used for the relief of indigestion. Determine the percent composition of sodium bicarbonate. That's it. It just says determine the percent composition. So what we have to do is we write the formula first. This is for percent composition. Percent composition. This one's not really, it's not in any way tricky. The math is really not very complicated. We started by just writing the formula which was given, NaHCO3. For each of the elements in this compound, we convert that number of moles, the number of moles present in 1 mole of that compound, to its mass in grams. So we have 1 mole of sodium. Where did I get the 1 from? I guessed. It's kind of hard to see, especially with 1. But let's go through all the rest and you'll see where it came from. 1H, 1C, and 3O. So where did these numbers come from? Yeah. How many there are? The subscripts. So we have 1, I should have written mole in here. 1 mole, 1 mole, 1 mole, and 3 moles. That's about the least legible thing I've done all day, and that's saying a lot. And for each of these, we're going to convert it from moles to, well, we're trying to find percent composition by mass. So mass, yeah, grams. And each of them is going to be 1 mole. That's how this is defined. What's the molar mass? That is, how many grams per mole in sodium? And how do you know? And where do you find it? Periodic table. What is it? You okay, Peyton? These got bigger towards the end. I don't know why, but. It's 22.990. You might have your periodic table out for this. It'll help you a lot. Hydrogen is 1.0079. Carbon is 12.011. Oxygen is 15.999. We're going to end up with several different masses. Well, 1 mass for each of our elements, and then we're also going to sum them all up. Okay, math it up. If someone wants to take care of the first couple, someone else the second couple, and then we'll add them all together afterward. And that'll be the second to last step, so we'll have another thing to do after that. Yeah. So what should someone actually do on their calculator then? Add all those up. And what is it? Does this kind of ring a bell? Does this adding together of all these ring a little bell? It's the same thing as this.
It's right there.
No, I had one.
What is the sum of these? Yeah. Yeah, sorry. Yes, you should multiply the last one by 3. Thank you, Haley. 47.997. Sorry. Okay, now add them all together, please. Thank you, Haley. +23 1 is 24, and 12 is 36, plus 48 is about 84-ish. 84.0059. So we'll call it, let's call it 84.01, just for sig figs. As I said, that's the second to last step. So now we found the molar mass. We found the molar mass, which is also the sum of all these. So the actual formula for percent composition is mass of that element over the molar mass of the formula times 100%. That's it. That's all it is. And so for sodium, we're going to do 22.990 grams over 84.01 grams. You see where both these numbers came from? Percentages are like this. Just like that test I just handed you out, it was out of 75 points. I put a score on there that was out of 75 points, so 60 maybe is what it said. That's not a percentage, right? 60 is not your percentage grade. 60 divided by 75 times 100 is. So in that case, that's what is 60 divided by, that's 80%, right? That's 8 or 4/5, which is 80%. 4 divided by 5, 0.8 times 100, 80%. So same thing with this. We have a part divided by the whole. That's what a percentage is. So for sodium, it's going to be this. For hydrogen, it's going to be this. I'll erase this now so we have a little bit more room. For carbon, it's going to be this. I didn't get an answer before, or at least I wasn't paying attention when I got an answer before. Sorry, forgot again. Do you see where I'm getting these numbers from? And this makes sense to you?
Yeah.
Anyone else? What will all these answers be? What's the unit going to be on all these? Unit, here used pretty loosely. No? Percent, yeah. Let's just get these to the tenths. That's probably not quite right for sig figs, but it'll be easier for me to write, and it'll have enough room. What is it for sodium? 27.3 for hydrogen. 1.2%, okay. For carbon. 1.2.
14.3.
Okay, and for oxygen. There's actually two ways to find it for oxygen. What's the other way we could do besides just what I have written here? What must they all add up to?
They all have to add up to
They all have to, well, as a percentage though, they all have to add up to 100. So we could just add these three together and take it from 100, but we're already doing this, so what is it?
19.
I don't think so. I think you might have just divided 15.999. It has to be all three of them. Times 100, so 57, right? 57.4, I believe. If we add these all together, we should get somewhere between 99.9 and 100, right? So 57.4 plus 14.3, that's going to be about 71.7 plus 1.2 is 78.9 plus 27.3. Yeah, about 100%, right? Maybe I did some bad math, but I think these add up. Will someone please just add it up to 100 real quick just to make sure that those are... Oh, 57.14. Okay, that's wherein lies the trouble. We did not get to empirical and molecular formulae. Who's going to be gone tomorrow? Everyone's going to be here, right? We'll do empirical and molecular formulae tomorrow. Bye. That actually will make it a lot.